So using like, okay. I think it's better to not use, because then we will have a look. So you can go ahead.
Okay, welcome everybody. Fantastic to see you in person after all these years. And I'd like to start right away so we can stay on schedule. George, why don't you come up and talk about the overview of where we stand, the status of the mission, and what we're looking at going forward.
Great, thank you, David. So this is the microphone too?
Yes.
Okay.
You can move these things around if they exclude.
There's the. See the
Black
cursor.
on black, and not seeing it.
That's going to be.
If you,
I'm going to try to get. Yeah, just get rid of that. So it's distracting. And just push a little. Yeah, thanks. Perfect. Okay, well, it's a great time for us to be in this building. There are memories from when we did a lot of the original reviews for TESS and the hardware and the software and some of the things that we did in the early and mid parts of the program. What I'd like to talk about today is just a general overview of where the mission stands and the plans that we have for the second extended mission. A lot of the things that I'm going to skim through are going to be covered in detail by the follow-on talks that other speakers are going to give this morning. This works. Okay. Well, this is an image that I think many of us are familiar with that actually shows the layout of the cameras that we had in one of the early sectors of TESS. And one thing that we've managed to do is with the full frame images from the prime mission to the current time, we've been able to decrease the time of the exposures, and that's really opened up an enormous amount of new types of science. We're able to do 300 million stars and galaxies in the 3 years that are coming up for EM2, and the 2-minute sub-images will be available for over 100,000 stars per year, and we're going to continue to use the 20-second sub-images for a more limited set. With the fact that we've gone to the 200-second FFIs, there's much less need for the 2-minute data, and we're actually going to be providing more emphasis for the 20-second data. And I'll come to that, and Roland will be talking about that in his presentation that'll follow afterwards. So and of course, this is, it's been our policy all the way through, and the fact that we're able to release the data even more rapidly is going to mean that the lack of a proprietary period is going to be an important part of the TESS science. Okay, this is a quick overview of the way we survey. I'm sure everyone in the audience here at least is familiar with this. And then we're going to, when we look at the ecliptic plane, we roll the satellite over 90 degrees and have the center line of the 4 cameras projected against the ecliptic plane. And that's been an important part of the survey, and that's going to be continued in EM2. So the étendue of TESS, just to remind everyone, it's currently the highest value of any operating spaceborne telescope, and it'll have that status until Roman launches later in the decade. This is a plot that I always like to look at because it shows as a function of magnitude from the HST guide star just how many stars and other objects we can access with TESS. All sky, there's about 400 million stars down to 18th magnitude that we can access, and then in a given sector, there's about 25 million. So this actually points out the incredible value that the full frame images have for the mission. The cumulative sky coverage that we've had for the 3 missions, or we will have for the 3 missions, are shown in these plots. This was the prime mission from what we obtained in 2018 and 2019. And then this was the first extended mission with sky coverage. We went from 70% to 89% sky coverage. And then in the upcoming EM3, we're going to, EM2 rather, we're going to be able to push that up to 97%. Roland's going to cover this, the details of this in more completely than I will. So the other thing that's important is that for many of the observations that we're making, the ecliptic pole regions are going to be have very extensive survey, and we should start to be able to move out to planets that have periods that are a good fraction of a year. So that's going to be certainly something that will emerge. And there's going to be some presentations of that information that Michelle Kunimoto will be giving in her talk. This is another really gratifying aspect of TESS. There's a very high rate of discovery papers that we've been able to provide from the mission and also from the user community. Again, it's because there's no proprietary period, that's a factor, but it's also the quality of the cameras and the effectiveness the spacecraft has given us in terms of the way that it has operated all during the 4 years plus that we've been operating to date. To give an idea of what this means, this is a plot that is maintained at the guest investigator office at Goddard, showing the number of publications that we've been able to have. And it's important that as of just last week, there's more than 1,000 peer-reviewed publications. So that means that worldwide, people are producing about writing 2 papers a day and publishing them from test data alone. And that's really unique among NASA missions. And so it means that for an Explorer class mission, we're certainly doing more than is normally the case. And the other thing is that a lot of the topics now are no longer just exoplanets. They never were, but the balance is shifting more and more to non-exoplanet astrophysics. During EM2, we're going to be changing, in fact, we've already started this month, the downlink plan to make room for the 202nd FFIs. This cartoon on the left actually shows what we have been doing in the orbits till we started that step. We were basically doing 2 contacts at perigee with approximately a day in between. Now we've changed to a mode in which we're doing a contact at perigee and also a contact at apogee. And so that means we're actually bringing down data once per week. And that means that we're going to be changing the cadence in which we actually analyze and deliver that data to MAST. And looking at the way that actually operates now, there are two operational aspects of this that we've implemented, and these are working beautifully so far. And we started this about a month ago to implement these as a regular part of the program. The first one is the use of TICA FFIs, which are being delivered to MAST as calibrated data in 2 to 4 days. This is through the work of Michael Fastenal and the folks who have been assisting him in this. And there's been a lot of great help that we've had from the team at MAST to make this happen. And then in the case of the the QOP, the processing there has been also been sped up dramatically, especially the step in the middle for the box least squared search now is being done much faster than was the case before. That step alone is 2 to 3 orders of magnitude faster than it was before. So that means we can count on delivering the data in approximately 8 to 10 days from the QLP. This is a listing of some of the user community targets that benefit from this faster dissemination of the TESS FFIs. And to give one example, for the case of exoplanets, the fact that we can get the data to the community 2 weeks earlier means that there's an extra hour per night for the follow-up work. And as you look down through this list, you can see the other benefits that come from this. Another way to view the scientific benefit of the 200-second FFIs is this this chart that was put together by Kevin Burge, showing as you go from right to left in those panels, what the Fourier transform or folded pattern that you would get for a 19th magnitude eclipsing binary that has a period of about 50 minutes. And you can see that as you go toward from right to left, you end up with, you see the spikes and the harmonics showing up more clearly. But by the time you've reached, I don't know, does this cursor work? Doesn't seem to respond. In any case, if you look at this panel here and this panel here, between the 120 seconds and the 200 seconds, there's really not much difference. So we're reaching, for at least for certain types of observations, a point of potentially diminishing returns by going any faster. But that's something that we'll be considering as the mission goes on. Okay, now this is a plot that Michelle Kunimoto will talk about a little bit more. It's basically what we expect for the planet candidate yields by mission phase, and going from upper left. This is the primary mission, then mission 1, then mission 2, and then a summation of all the results that we have for planet candidate yields. And the key thing that has emerged from this is if you look at that gray area in the primary mission for 2-minute data, that was a critical part of finding many smaller planets. But as the mission has gone on, the utilization of the 2-minute of the FFIs has meant that most of the benefits for planet identification will really come from the FFIs. So we went from 2,300 candidates to 1,800 to 1,300 as we step through those 3 initial phases. And so the expectation is that we'll be operating at about 1,800 per year, yielding about 1,800 per yield. And after in the 7 years, we're going to have somewhere in the range of 12,000. So this is some information that is developed in a lot more detail in Michelle's paper in AJ. And this is again another item related to Michelle's work that she'll be talking about later this morning. So we've also been able to discover many new types of objects in all the categories that are shown in this list. And there's thousands of solar system objects, thousands of explosive and variable extragalactic sources that we've been able to contribute to, and variable stars, especially areas like astroseismology, have been a really high scientific yield for TESS. For observations of asteroids in the solar system, this is work that was done by Deb Woods and her group at Lincoln Lab. There's almost 43,000 unique objects that have been reported to the Minor Planet Center. And this shows the distribution and ecliptic coordinates of those objects. They're a treasure trove for astrophysics as well. This is Adina Feinstein put together a collection of these results in her paper. You can see that this is going to benefit greatly from the 22nd data. So, and then moving out toward extragalactic sources, this is a plot from Michael Fastow showing at more than 800 bright type 1A supernova that have been observed by TESS. And this is something that Michael will have a chance to talk about in more detail in his presentation. And then another thing that's gratifying is that in the Astro 2020 report, this is a plot from that document. The fact that there is this relatively unexplored region in space, in temporal space from 1 to 10 days is something that TESS is going to be very effective at working through. And so there's a lot of new discovery space that we'll be able to utilize. And in terms of synergy with other missions in the upcoming years, these are 14 examples of the types of things and the associated mission that TESS will be able to contribute to. Some of this is in exoplanets, but a lot of it is in areas related to astrophysics in a broader sense. And this is the timeline for these synergistic missions. And this is what's shown here in this block. You can see all of these different missions we've been operating currently with the KASC, all during the baseline mission, for even more so the extended mission. Hopeful that Rosita will be able to continue to start operating again in a broad way. Of course, Webb and LIGO, of course, going to start the Rubin Observatory. And then in the EM3, we'll be able to move into a more full operation with Ultrasat, potentially overlapping Payload and the GMT and the ELTs when they come online. So it's a very gratifying set of circumstances. You know, TESS has come along at just the right time to enable a tremendous variety of new scientific initiatives, and we want to continue this. This is an ad for 2 postdoctoral positions that we're going to have at MIT. So this was just posted earlier this week, and please contact me if you're interested. So these are the takeaways from the mission. Basically, we're really happy that this has been a continuation of the performance of the satellite, and the second extended mission now is well underway. Thank you.
Excellent summary. Thank you, George. We have time for a couple of questions.
The way we do it, can just stay in your seat and ask the question. The speaker will be kind enough to repeat it so that people are not.
Okay.
One online. Is it a chat or is it?
Would you like to comment on the recent segment?
There's a bit of information that NASA has posted on this, and I couldn't add anything more than what's already been made public. It's just the satellite is out of safe hold and is working, and it's being restored, and it should start operating shortly. So,
How many days are lost?
I don't have a specific number day to report.
Anybody else with a question? Right on time. Thank
Okay,
you.
thank you.
Roland? Let's hear about some of the details now. Don't mention the ball. Version 2.
microphone. Move this downstairs. It's down there somewhere.
Excellent, thank you. I'm not much of a yeller, so if you guys don't, if I start fading out with my voice and you guys in the back can't hear me, just give me the signal. I'm going to spend a few minutes talking about the payload status and a little bit of projection as to what we're going to be doing in EM2. And I'm going to try desperately to actually use this thing. These are the basic topics I want to touch on. Instrument and operation status. Spend a fair amount of time on EM2. Talk about attitude control system updates, which may impact observations. And then a few insights into cosmic rays and TESS. So overall instrument and operation status, cameras are fine. The focus is stable, the temperature is stable, the CCDs are doing great. You know, we lose a few pixels. Spacecraft stability is excellent. The ground communications is working well. I'll get back to that in a minute. Mission planning and telemetry processing processes are routine. We have a new operator, Sean McNeil, who may or may not be in the room, who's been a great boon to our group. And when we went into EM2 this month, it was seamless. We were well prepared for that. Speaking of EM2, I'll just touch on where we will be pointing some numbers of targets and talked about how we're handling data on board. The pointings that we put together were calculated given the goals of 95% of the sky observed at least once after EM2 and 80% at least twice. And I'll have to note that it wouldn't be a TESS science team meeting if I didn't show a slide that George already showed. So you've seen these things on the right. We're doing the same types of observations as in the prime mission in EM1. We're either pointing north-south or we're pointing in the ecliptic. You'll notice these gaps here in the maps. Those are from the gaps between the CCDs because we're always pointing at the same ecliptic latitude. Those regions don't get observed. In EM2, we're shifting the fields by 1.5 degrees so that we cover those at least once. Similarly, there's a hole about 3/4 degree in diameter at both ecliptic poles. We're getting that out by rotating the fields around the bore side axis by about 1.5 degrees in EM2. So all of those things will become will have been observed at least once. So these areas here are observed once as opposed to observed zeros. The ultimate answer George has already given you. 97% at least once, 84% at least twice, and 68% of the sky at least 3 times by the end of EM2. Just for the details, in year 5, we're going to finish the northern ecliptic hemisphere and start a southern survey. In year 6, we'll do we'll finish the ecliptic, at least observe the part of the ecliptic we didn't observe last year, and do a northern survey. And then in year 7, we'll finish the north, do a little ecliptic in between sectors of the south. Now, in extended mission 1, we had 600-second FFIs. We allowed 20,000 targets at 2 minutes and 2,000 targets at 20 seconds. In extended mission 2, as George mentioned, we're going down to 200-second exposures. So it's really not necessary for us to carry 20,000 2-minute targets. But there was a lot of interest in the 20-second targets, so we upped the allocation by 50% for 20-second targets. Now, the targets that we're going to be observing are broken up into these candidate target lists. The standard set of bright stars, photometric precision assessment stars. We're allowing 6,000 GI targets in the initial allocation. But the way the system works is once we've gone through all of the CTLs to pick stars. If there are any slots left over out of the 13,000, we'll go back and select whatever we need, whatever's left over, starting with GI. We have an exoplanet target CTL, which is made up of all known TOIs and all known CTOIs, and all planet candidate TCEs, and Katherine can tell me exactly what those are, what that qualifies at, but it's things that are borderline, they're not quite TOIs yet. And we've also included a subset of the original exoplanet CTL, which was all sky, but we included only those that haven't had a chance to be observed yet. So if you look at this map of ecliptic latitude versus ecliptic longitude, you see all the targets that could have been selected, but hadn't, all the targets that have not yet been selected or were not possible to observe. You can see the chip gaps at 18 and 54 degrees latitude. You can see the band on the ecliptic that wasn't observed, and that region of the sky that we haven't gotten to yet. But the bottom line on all this is that all the GI targets will be observed. If it can be observed, meaning if it's on silicon and not near a bright star and not crowded and not excluded for other technical reasons, we'll observe it. There are more than enough targets to cover everything in the GI. I'll also note that we have director's discretionary targets, severely underused, both at 2 minutes and 20 seconds. Come on down if you have targets. So to go a little bit towards what George was speaking to earlier, we're looking now at the fill of the onboard solid state recorder, the SSR. And the column you want to be looking at is here in green. In extended mission 1, in an orbit, we filled the SSR about half full. So when we came around and did our data dumps, we could dump half the data, dump half the SSR, and we had a backup contact to dump it if there was a failure. In extended mission 2 with the 202nd FFIs, you can see that the FFIs now are suddenly taking up 85% of the SSR. And the key number here is that 97% in a full orbit. You kind of want to have the SSR at 50% when you dump, just for safety, which motivates the change that George mentioned earlier, that we are now dumping data at apogee and at perigee, but we only have one contact at each point. So by using the apogee contacts, we make sure that the SSR is about half full. Now the thing is that the DSN contacts are generally pretty reliable, but they're not perfect. There are times when the contact is incomplete. There have been a few instances where if contact has failed entirely, it's a handful over the mission. But just in case we have contingency plans in place, in case there's an incomplete contact or a failed contact. In the case of an incomplete contact, we know what we got on the ground, and we can command the spacecraft at one of these S-band opportunities to remove those files from the SSR. Remember, the instrument computer is basically a Linux box, and you just do RM blah, and it's gone. In the case of a failed contact, that the SSR is going to be 50-ish% full, there's not much you can do at that point. One could consider going in and surgically say, oh, that data isn't important, let's get rid of that, but we're not going to do that. The flight computer naturally shuts down observations when it gets 97.6% full. So we'll just let it do that in that situation, and you lose the last 1-ish, 2 days worth of data if that happens. Okay, that was the run through of EM2. We'll talk about the attitude control system. This is a MIMU. I have to remember that it's MIMU because it sounds like Mima, apparently. This is the inertial measurement unit, the gyroscope, as it were, on board the spacecraft that measures the rotation of the spacecraft. It includes a ring laser gyro, I got this, and inside of which is a laser that has a limited lifetime. So you really don't want to be relying on this thing long term. So we're making every effort, our friends at Northrop Grumman are, to remove the MIMU from the ACS. And we've been testing what is called ACS patch 5.10 for most of this year to allow fine pointing without using the MIMU. Now, we've been doing these tests between the contacts at perigee that we used during EM1. We don't have that in EM2, so I'll get to that in a moment. But the results do look promising. Slow. These plots, I may have shown them before. You don't have to understand them completely because I don't. This is the integrated power spectral density of the spacecraft jitter. This is the way that the ACS folks measure performance and define requirements. And we have a set of requirements here. At 1 minute, we should be below 2 arc seconds, 3 sigma. And at 1 hour, we should be below 0.06 arc seconds, 3 sigma. And in 5.9, which is the current, is the current ACS patch, we're meeting that requirement beautifully. And you can see at 5.10, we're doing it as well. So that's all looking promising. The question is, what further tests are we going to do? We're still in discussions with Northrop Grumman about what to do there. Then the question is, when do we do these tests? We don't have the space between the contacts anymore, so we can carve out a region a day before perigee and just use that and heck with your science. Or we could throw a whole orbit at it if we think that we're not going to impact the science significantly. These are questions that are under discussion. We're working with our friends at SPOC to look at the impact of 510 on photometric precision. So, stay tuned. Okay, so that's that. Let's talk about cosmic rays. Cosmic rays hit TESS. They hit the CCDs. You'll know that the 2-minute and 2-minute observations and the FFIs use cosmic ray mitigation on board to remove the cosmic rays. And I'll get back to that in just a second. But the 20-second data that we've collected does not. So it comes down pure, and we rely again on our friends at SPOC to do their Kepler-based magic to identify and remove the cosmic rays from your data. All of the data information about the cosmic rays is included in the target pixel files, so one can go and mine them. And just for a scale, we're expecting a cosmic ray every 3 20-second exposures or so. They do bunch up, don't they, Emily? So I had a student this summer looking at the cosmic ray characteristics using the 20-second TPFs over a bunch of sectors. And it was a bigger job than I was expecting, but he did come up with some basic information. This, for example, is the rate of cosmic rays detected per hour in all the targets in one of the CCDs in sector 44. And you can see that it's relatively flat. There's that spike there, which happens to be the coronal mass ejection that happened last October, the so-called cannibal CRM. We saw that quite clearly. I'm showing this because it's the coolest of the plots. If you look at the other sectors, they're flat as a board. It's sort of disappointingly dull, but there are details to go into this. Now, we've made a little movie of all the cosmic rays in one TPF in one sector. So there's about 20,000 15 to 20,000 cosmic rays in this little movie. And I'm just showing it to you here so you can get a feel for what the shapes are. They're mostly straight. You got some individual ones. This is matplotlib, so you have no idea what the intensity scale is. So it's auto scaling the whole way. But the key takeaway here is most of these things either start outside of the aperture or end outside of the aperture or both. It's just these apertures are not big enough to fully characterize these cosmic rays. It's hard to draw conclusions about an entire cosmic ray based on just a segment. You don't even know which segment. So what we've done is we've allocated 64 33 by 33 pixel boxes in sector 58 coming up in a couple of weeks at 20 seconds. So we can get the full scale of these cosmic rays. These data will be marked as cosmic ray target and will be made public with the rest of the 20-second data. There might be a special table that's distributed with the data release notes for that sector. I haven't quite worked that through. Okay, the other thing about cosmic rays is that it turns out, thank you, Dan Huber, that the 2-minute light curves for a particular target are noisier than a stacked light curve created from stacking 20-second light curves. And he published a paper et al. In last year And this is a figure from it. Now, I'm going to preface all this by saying, I didn't do all this. Andrew did all this. And I'm going to stand here and present some of Andrew's work just because I want to make a point at the end. But if you have questions about the details of the analysis, I'll listen in, but you want to be talking to Andrew. Those of you online, sorry. Thank you, Dave. So here you have a measure from Dan's paper about how more sensitive stacked 20-second light curves are than the 2-minute light curve. And you can see that it's a fair fraction, and it depends on magnitude. Andrew did a quick analysis using Newton loopy, showing the same things. It's the same data, no calibration, no calibrations or systematics. Just stack them up, stack the 20 seconds, and you can see the 2 minutes, and you can see it's just noisier. Now, one of the cool things about Daniel's paper is that he looked at the two halves or two orbits in sector 34, one of which was jitterier than the other. And that's the difference here between these two curves. And it's about 10% difference just due to the different jitter performance in the two orbits. I haven't looked in detail as to how much jittery it was or what metrics to use for those. But there is clearly a difference. And that leaves us to it's unescapable. The conclusion is the cosmic ray mitigation on board. Now, to remind you, cosmic ray mitigation on board looks at the values of each pixel in sets of 10 2-second exposures. It looks at those 10, it throws out the highest, throws out the lowest, and sums up the rest on a per pixel basis. And the idea is that if a cosmic ray comes along, like that beautiful cross of the, gosh, that's totally unreadable. That high point there would be representative of a cosmic ray. It would be eliminated, and you wouldn't see the. But in the presence of spacecraft jitter, that could be a real data. This is where Andrew. I'm getting some echoes. I won't let it bother me. Ransom simulations of an artificial using a regular Lissajous pattern of jitter, and you can see that the CRM data are noisier than the non-CRM data. And then he used real spacecraft jitter, and oh yeah, it's a lot noisier. And the takeaways from his work are jitter and CRM means extra noise. The less regular the jitter, the more the CRM impacts it. The Lissajous was kinder to the noise than the real spacecraft jitter. And the third one is added noise is worst when the time scale of the jitter is comparable to the time scale of the cosmic ray mitigation. And I'm going to focus on that line for this last slide, because it turns out if you look at the power spectral distribution of the jitter in the spacecraft, it's always had a strong peak at 25 seconds, which is really close to 20 seconds. So this is interesting. It'd be interesting to explore what could we do? How could we improve the 2-minute precision if we adjusted the CRM timescale? So what we'll be doing, hopefully soon, we're investigating it now, is the possibility of collecting raw 2-second data for a handful of targets, and then subjecting it to ground analysis at different cosmic ray mitigation cadences to see how the photometry improves. So we're still talking about it. We're slightly distracted at the moment, but next month I'm hoping that we can get some traction on whether this is even possible. Now, speaking of these possible, it is possible to change the cosmic ray mitigation parameter from 20 seconds to say 40 or 60. It's just one number in one file that's uplinked. It's easy to do, but we really have to think through all the ramifications of suddenly saying that data point is 80% of the real flux, and now it's 90% of the real flux, and make sure that everything downstream is properly propagated. And I think Dave walking up here means I can type, let's do that.
Question from George.
Yeah, this is actually
It's not the question.
related to the two contacts in orbit neither I nor Roland mentioned the fact that we're actually getting an extra day of almost a full day of observing under those circumstances. So that means 2 extra days per sector on average. And so if there are overflows and things like that we have to deal with in the on the state of the quarter, that means that the total exposure time we're going to have as the issue is going on, we have more margin.
So George's question for those online was a statement that he and I both forgot to mention, that the time between the contacts at perigee is now freed up to do actual science. And so we'll gain 18 to 24 hours per orbit of observation time. So that's a day and a half to 2 days of science per sector.
Anything online? No.
Yeah, and nobody cares. Oh, thank you,
Got a
Doug.
cool movie.
Yeah.
All right, let's see. Hannah? Josh is going to do it. Going to hear from headquarters. Josh is deputy program manager.
Program scientist. I don't know slides. Yeah. Okay. All right. So I don't have any slides. I just wanted to introduce myself to those of you I haven't met yet. My name is Joshua Pepper. I am the new deputy program scientist for TESS at NASA headquarters. The program scientist, NASA Jen Condell, is unfortunately sick, and she sends her regrets. She was going to be giving this talk, but I just want to say that we're so excited about the performance of the TESS mission. It's been working fantastically, and there's been enormous contributions from everyone involved in the mission, from MIT to CFA, MASC, the SPOC, and NASA Goddard, all of mission partners. And we're very pleased to see just how much benefit this mission is providing to the exoplanet community as originally envisioned, but also to the full array of astrophysics, and even outside of astrophysics, things like planetary science and solar system science that TESS is doing these days. So we're looking forward to this. We are in the process of completing our final letter of direction to the TESS mission for the extended mission 2. There's been some delays on that because of personnel changes up at headquarters, but we're working on getting that done very quickly. And once that happens, then Hannah will step down as program scientist, and I will become to be deputy, and then I will become the program scientist for TESS, and look forward to working with all of you going forward. And I do want to mention just one point that George briefly mentioned during his talk, which is this the TDAM program, which is the Time Domain and Multi-Messenger Astrophysics Initiative that was recommended by the decadal survey, and which everyone realizes TESS is such a valuable contributor to. And I want to mention that there was a conference about a month or two ago to discuss what NASA is planning for the TDAM program. And there is a white paper that is being written up to talk about what kinds of science is relevant to TDAM astrophysics, and there will be a public comment period for the whole community to contribute your thoughts on that, about the roles of different science areas in time domain and multi-messenger astrophysics, and instrumentation and missions and their relevance to time domain and multi-messenger astrophysics. And so I encourage everyone to keep an eye out for that white paper, and to offer comments to say how you think things, especially like TESS, can contribute to that. And that's basically all I have.
We have time for a question or two. Want to know what's going on at headquarters besides trying to decide how to cut everybody's budget?
Look, there's only so much money to go around, and there's only so much we can do with that. All right.
Anything online? Thank you, Josh. Anything online?
Thank you.
Well, now, Knicole Cologne is going to tell us about everything the private science does, GRI office.
All the things.
Lots of stuff.
Okay, and I'm gonna stand in front of the podium because I'm short, so, but I'll speak loudly. Is it good? Oh. Is it playing slideshow? Yeah, see, it's default. Not bad. Enter. Okay, perfect. Yeah, and I'll speak loud. Okay. Yes, so it's been a while since I've been in Boston in person, and Josh Pepper mentioned a lot of personnel changes at headquarters. There's been a lot of personnel changes at Goddard too. So that's why I wanted to start off by introducing our team and also generally what we do here at Goddard. So yeah, I became the project scientist earlier this year. I'm also still the lead of the guest investigator program, formally speaking. But we also have Allison Youngblood here in the audience, who's our deputy project scientist. She joined this year. Christina Hedges is the deputy GI office lead. She's in the audience. You'll be hearing from her next. And then we have other team members. Rebecca Hounsel and Tyler Pritchard are also here from our team. And then we have other folks online. And Tyler and then Knicole Sankey, they're both new this year. Actually, Dustin's new. Basically, everybody's new except for me and Rebecca. So lots of changes though in everybody's roles. And so that's why I wanted to just say, okay, who are we? What do we do? Our project science team, we really interface with all the mission partners. So between TESS science, operations, Josh mentioned the budget as well. So everybody, we work with everybody. And we also oversee the grants from the GI program. So if you ever have questions about grants, that's what we are here for. And we lead science communications, so communicating science to the public. And then our whole GI team, again, Christina will go into some of the activities, but our GI team basically interfaces with the scientific community and also does some public outreach, but interfacing on many levels. So that's our team in a nutshell. And so I just wanted to basically call out a few points here about some of the things I just mentioned that we do. Science communications, we work with, well, we have a team at NASA Goddard led by Claire Andreoli, but we also work with the Exoplanet Exploration Program Office. They maintain our status update here of confirmed and candidate planets, which is always fun to see updates too. And they make other fun products. But we have a whole slew of stories that get put out by our NASA team. You're not meant to read this. This is just a sampling of story titles that have come out over the past few years from the mission. And it covers everything as George was saying, we do everything with TESS, right? It's not just exoplanets, it's all the things. And so we have a great sampling of that here in terms of exoplanet to stellar astrophysics to extragalactic science. And so what does it mean to have your work featured by NASA? There's a couple things this means. Basically, what you can do is put in a media request if you ever think your story is newsworthy. Hopefully, everybody thinks their story is newsworthy. You know, all our science is exciting. But what our team will do, they do have to filter. They can't cover everything. But that's okay. If our NASA team cannot support your work and put out a press feature on it, maybe your university can, and then NASA, we can promote it still. So that's another avenue to get more publicity for your work, because we want everybody to know about your work, and then also, you know, to make sure that TESS still gets its day in the sunshine here. So George already showed the publication rates. I did want to highlight, I looked at the last talk I gave at a science team meeting in August 2020, when EM1 had just kind of started, and that was how it started. You know, we only had 263 papers. How it's going, we're over the 1,000 mark threshold. So I just love that comparison, and I wanted to emphasize again also the change in topics, as George pointed out, exoplanets versus astrophysics. Astrophysics is a big lump here, but it's basically anything not exoplanets, and it's slowly taken over. But that's a good thing. Again, it's showing the versatility of TESS. Okay, so something else that we do, if you haven't seen us around at things like AGU or WS, we are there. Our team at Goddard often has a table with the NASA booth or has our own booth separate as well. And so we do all kinds of stuff. I'm not going to read all this information here, but we are there to interact with everybody. And so we'll have workshops, hyperwall talks, all the things. You'll hear a little bit more about this from Christina, so I don't want to spend too much time on it. But we had actually our first AAF Splinter back in person was in June of this year, so that was great to be back. We put in a proposal for another evening session for this coming January, so stay tuned. And that was my whirlwind tour of just some highlights, basically, from our team at Goddard. Again, Christina, you'll be hearing from, will go more into GI activities, but I basically just want to point out that as project scientists and with Allison Youngblood as well, we are here to, interface with everybody, essentially. So if you ever have questions or concerns about anything, ranging from the GI program out to science communications, public engagement, scientific engagement, anything, don't hesitate to reach out, and then hopefully I can give Christina a little more time because I think I was early.
Well,
right.
thank you.
Thank you.
Any questions from the audience? Moving online? No? Well, thanks again.
All right, thank you.
Yes, and that gives a little extra time for Christina. We talk about the GI office. I'm sure everybody's interested in the GI office, so we're looking for projects that might bring. Currently, we'll bring new data, but might even bring some months.
Hi, everyone. Thanks, Nicole. Yell if you can't hear me. All right. So, hi, everyone. My name is Christina, Christina Hedges. I'm the new Deputy Director for the General Investigator Office at TESS. And I'm just going to cover a few little highlights from the GI office. Please shout it out if you have any questions. So some highlights from our recent cycle 5. We completed cycle 5 quite recently. We have allocated over 58,000 targets for GIs at the 2-minute target level. We've also allocated over 14,000 20-second targets for GIs in cycle 5. We gave out almost $3 million in funding for GIs to complete their science. And over 600,000 of that was for ground-based follow-up. That was actually more than we thought we were going to allocate because we had a lot of really great ground-based follow-up and support programs. We had over 101 proposals submitted, selected 49 of them, which included 12 mini programs. Mini programs are 2 pages of proposal. They're usually used for 1 or 2 really interesting and exciting targets, and we don't hand out funding for those programs. So if you have targets where, oh, I really desperately need this for cycle 6, remember mini programs are low effort and high impact. They'll get you your target. Some highlights on what we selected. So I've got a few bar charts on the screen now. I've got different proposal types. We have that mini kind of proposal, people who want to use postage stamps, people who want to do ground focused or have some ground follow-up. We have FFI only, and we have joint programs. Joint programs here are joint programs with NICER, SWIFT, or Fermi. I'll talk a little more about that in a moment. You can see in black what was submitted and red what was accepted. You can see that we're pretty good across the board, pretty even number across the board there. We have different proposal types. This is interesting. So we have stars, exoplanets, extragalactic, solar system object, and other as a way for proposers to define what kind of program they're putting in. We get a lot of stars proposals. TASC really impacts the stellar astrophysics community, and so we get a lot of stars proposals. We obviously get a lot of exoplanet proposals. We're still getting a lot of extragalactic proposals and 1 or 2 solar system. Finally, we've got different proposal efforts. So mini, again, 2 pages, no funding, just get your targets and run with it. Small, which is our biggest category. Small are for efforts. I think this is a 4-page proposal. You can get a moderate amount of funding to do your science. Then we have key project, that's a many-year effort, and large, which is 6 pages and a little bit more funding than small. You can see we mostly get small proposals. This is for people to get stuck in with our test data. This is what we get the most of. Some highlights, so we selected one key project in cycle 5. Congratulations, Diana Dragomir. We selected TESS Reaches for Cooler Planets. This is a key program, so multi-year effort, and they're going to be looking at extracting long period planets from the prime mission EM1 and EM2. We're excited to see the products that come out of this great program. We also selected 3 joint programs. We can join up with NICER, SWIFT, or Fermi to look at both the optical with TESS and then some higher energy astrophysics with sort of UV and X-ray other missions. If you have any interest in putting in these kind of joint proposals, please reach out if you need any help at all. We're really happy to help you put in these kind of proposals or design these sorts of programs. So we've got some which are both joint with NICER and SWIFT, and those observations are actually being undertaken right now. We also have a targeted opportunity program with SWIFT. Please reach out if you want to learn more about how to both propose for this or work with this kind of joint data. We'd be really happy to chat with you. So save the date for cycle 6. We're expecting the cycle 6 call for proposals will be released in January. And then we're anticipating that cycle 6 proposal deadline will be in April next year. The pointings are available on the MIT website for cycle 6. Bear in mind, they may change a little. But the preliminary ones are up on the website. I know that lots of people have mentioned this already. We're going to have some sectors, 3 sectors, 75 to 77, are going to point directly towards the ecliptic. If you have any awesome solar system science that you're planning to do with TESS, this would be a really good cycle to propose for that kind of science. Looking in the ecliptic, you can get a lot of really cool solar system objects. TESS publications continue to increase. The community is fantastic at putting together brilliant TESS publications on a range of topics. Here they're split into 2, exoplanets and astrophysics, and you can see that TESS actually impacts the astrophysics community now even more than exoplanets. And this has been true since EM1. We're doing more for astrophysics than even are for planets. TESS is also really good for our global community of astronomers. Here's a map of the lead author affiliation for people who are published with TESS. You can see that there's a huge contingent of US astronomers publishing with TESS, but it really is global. TESS has publications from all around the world. And we can even split this into state. TESS has contributing authors from all around the US. You can see where one or 2 of them come from, the top 3 states you might all be able to guess. But TESS really pulls together a community across the US and the world. TESS also has a huge impact on early career astronomers. This is the number of proposals by years from PhD. So this is our PIs for our GI programs. You can see that there is a huge contingent of early career astronomers who are successful PIs and GIs for TESS. TESS really impacts early career astronomers, and I want to remind us of that. It's excellent. So the TESS GI office is here to support you. Please reach out whenever, if you need any kind of help with TESS. Remember that we're always doing the help desk. So no matter what, we're always here to answer your questions. We're also always doing proposal reviews and making sure that everybody has access to funding for TESS research. At the moment, we're now looking into building more tutorials to work with TESS, including on a focus on joint observation. So again, care about joint observations, reach out, and we'll be putting together some new tutorials for you. We're working on an upcoming data workshop that I'm going to tell you about in just one moment. And please check out our news bulletins for TESS. We put them out really regularly, and lots of our science is getting highlighted. Check them out on our website. Soon, we're going to be looking into updating Lightcurve as a way to improve user experience. I know that lots of people in the room and online use Lightcurve as a way to access the data. The GI office is going to be soon putting a focus into how we can improve the user experience for Lightcurve. We're going to be making some more tooling to work with TESS data, and we're going to be looking at different kinds of background tools to try and help our community get involved in TESS data. And we'll be updating the GI website shortly so that it's easier to access some of the information that you need. We're absolutely here to support you. Please reach out. As Knicole said, we've got quite a few fresh faces inside the GI office. We've got lots of expertise on exoplanets, but also extragalactic and transient stuff. We have expertise on how to work with Swift data. We have 2 new GI scientists, Tyler Pritchard and Knicole Skanka, who are really excited to work with you if you have any questions. Okay, finally, so please look forward to the TESS workshop at the AAS. We're going to be running a data workshop at the AAS. This is going to be a full day on a Saturday. This is pitched at anybody, whether you are a regular user of TESS and you know exactly what you want to do, or if you're a brand new user of TESS. The format is going to be a morning that's going to have a few talks about not only what TESS is, but how to propose, how to get money to do TESS science. There's going to be some hands-on tutorials about how to work with the data and how to do systematics correction. And then the afternoon is going to be a hackathon where you're going to be able to work with the experts. All of the GI office is going to be there to work with everybody. And you can just bring the target that you want to work on, the kind of science that you want to do, work with us as experts and ask your questions live. So yes, interactive data workshop. Please come, bring your students, send your students, all welcome, any level. I think that is my last slide. So I'm going to leave this open. This is AAS, Saturday, January 7th. Please let me know if anyone has any questions.
Thank you for that very nice summary of all the great work that the GI office is doing. And if anybody has a question, here's your chance. Get one online. One online, what is it? Go ahead and read it.
Are TICA FFIs available through TESS Cut? I think this would be a great question for people who work at Mass, but my understanding is no, TICA FFIs are not currently available through TESS Cut. But they are apparently working on it.
Yes.
I'm so sorry.
Will it be broadcasted online, the workshop?
So the workshop will not be hybrid. However, we will have a lot of the materials posted online afterwards. So it won't be hybrid, but you'll be able to follow along with a lot of the materials, like the tutorials we'll post online, and we can absolutely send that around to people and put it on our website. But the event itself won't be hybrid, mostly because it's really difficult to do a hybrid interactive kind of hackathon event.
But Seattle is a lot closer to Japan than Cambridge. Anything else? Okay. So, you jet lagged, huh?
No, it's good for a few days. It's not jet lag.
Starting on,
It's not night in Denmark yet.
Alex is going to tell us about the enormous effort from the astroseismic community, which I think may account for a large fraction of the.
I think this astrophysics is at least supported by the publications we do in.
Yes.
PowerPoint is probably the best that you can use.
So we're going to hear about TASC, and I hope to hear a summary of the TASC workshop.
Well, you asked
the
me.
first one I missed of all of them.
Actually, me too, because I was asked to by Dave to give an overview of TASC and the workshop this summer for TASC6, TASC13. Sorry.
2 points. You can move the mouse.
Yeah, and how do I shift just indicator here? Okay, good. Thanks a lot, Ali. But I actually missed the workshop in the airport on the way to the conference. I was tested positive for corona, so I had to turn in the airport, and I was not affected by corona a lot. So I actually followed the conference from home. So when I now report on some of the aspects, it's not that I actually didn't attend the talks. But I will give you a few highlights of that workshop also. George was there, among others, in this room and online. Let me just start with, because there are some new faces here, the TASC acronym is actually, let me see, it doesn't go forward here, are we? Okay. It stands for TESS Astroseismic Science Consortium. What's called TASC is the TESS Astroseismic Science Operations Center. It sounds like a big center. It's actually a few people at Aarhus University who are maintaining a web page, data access, and coordinate activities in relation to astroseismology. This was built on the success in organizing the Kepler astroseismology. And it's a very diverse group of people that are included in what we call TESS, TESS. Some people are closely related to the work, others are loosely access the data, but it's very clear that the organization of the astroseismology activities have opened up also for a lot of young researchers, students who get access to data and to get access also to discussions with lead researchers and the community in general. And what is astroseismology actually? This is the study of stars, the interior of stars using the vibration frequencies. And in order to do that, this was, of course, very clear from Kepler, that if you really want to do that in a systematic way on high accuracy, you need very precise data on very extended periods. And this is what Kepler could give us in a restricted part of the sky. And TESS is now, of course, the major database for astroseismology in all over the sky. We, of course, also still do observations using ground-based facilities and other space observations, but this is actually very clear that the impact of data like TESS is enormous for all that research field. So that's of course what the community is doing inside TASC. We work on analyzing the TESS data, select targets in these many different groups. Also outside, of course, the organization here, the astroseismology is widespread. Time-series spectrometry we also analyze on the FFIs, and we produce data products that are optimized for astroseismology. And these are open data that people access to the TASC. One of the major activities in TASC is organizing workshops. We actually have a workshop every northern summer. We have once been in Australia in their winter. It rained the whole time. It's not a good commercial for Sydney, but a great conference, by the way. We didn't have workshops in 20 and 21. So Leuven were on standby in Belgium for 2 years. And then finally in 2022, the community could meet again in Leuven, and more than 165 people attended that workshop. We also already have decided where the next workshops will be, and this is in Hawaii next year and in Portugal in 2024. Yes, I have to stay close to this one here. Okay, I'm locked to this. Yeah. So let me just also mention that these workshops are the major workshop in astroseismology for the whole community, and this is not strange that it's then linked to the data from Kepler and TESS. So, well, the organization is a lot of working groups that are coordinating things, but also what we call coordinated activities that are providing across the workshops support for the activities we do. And it's also within here that there are people who sign up to lead the organization of the workshops. So the rest of what I will present here is some highlights from this workshop. Of course, it's a whole week, lots of talks, many posters. It's impossible to give all the highlights, and I will therefore focus on TESS. There was a lot of Kepler stuff also, but I will focus on TESS and give a few examples of the things that the TESS data allow us to study when we discuss the details of stars. And here you see the photo. There were many people also online, including some of us that, as I said, could not attend because of Corona. And there were also people in hotel rooms that could not attend the conference. They got sick while they were there. So, I mean, this is, of course, what we have to do nowadays. But there were many happy, and you see George here. So it was so nice for those that arrived there. I have heard to be back on a real workshop. So I will just quickly go through some of the highlights, and I have listed here all the talks. I don't expect you to read through all of it, and there could be some exciting titles that you would like to hear more about. If you want to actually even see the talks, they are all recorded, and you can go to the TASC webpage and you can download all the slides from all talks, including recorded talks there. So if you really want to get the detailed information, please go to that webpage. It's you have to sign in, but it's open for everyone. So if I skip something that you thought this was a highlight from the title, then just check that on the TASC webpage. But I will just say here on the first session, which was on missions, and George gave a status of the mission. But two things. There are actually some of the data that you can say are optimized for us in astroseismology. How do we actually work on that? How do we create the data products? And then also there's a lot of work going on classifying the stellar variability. So you don't have to look through the light curves, but use also machine learning to classify many of the light curves, so you can select special types of oscillators or other type of variability in the data. And this is again open for people to use. Some of it is also transferred to some of the data to MAST. But the first, this is by Rasmus Handberg, who is the responsible for a lot of the data processing and the catalogs at Aarhus University. And there are also papers on this photometry. But one of the things that are clear is that although we are delayed because it's a huge job to process all these data, there is a lot of light curves that are processed also from the database at Aarhus University that you can access through TASC, not through all sectors yet, but it is coming now. But one special type of photometry that we are very interested in, because it's on really very bright stars that are completely saturated in the data. But we want to combine this with ground-based radial velocity studies that are in seismology, where you want to detect meters per second oscillation. So you need the really bright stars, and you can do halo photometry to quite nice accuracy. And there are some data here where everything is saturated in the center, but even the scattered light from the star can be measured to an accuracy, so you can do a nice light curve. And this is work by Tim White that you see here. Then for the classifier, this is also within this working group. There's a lot of the stars, as I said, have been classified. There are more than 100,000 stars being classified in the data set. The second session was on compact pulsators, and this has been something that couldn't really be done by Kepler, because there were so few of these compact stars in the field of view. And the other thing is that the sampling rate was in Kepler 1 minute, and some of these are oscillating so fast that you need the 20 seconds. So with the opening up the 20 seconds, although some of these stars are faint, their amplitudes are in some cases so large that you can really detect the oscillations of white dwarfs, sub dwarf stars, and this is really something that is beating a lot of the data we have from ground. Searching for new examples of pulsating white dwarfs, there was a nice presentation of many of these different types of instabilities that where you have white dwarf oscillations. And a lot of the work in this working group 8 that are focusing on this has also been to really find discover new versions of these many different types of stars. And just as an example, you can see the title of the paper there. There's 74 new versions of these ZZ stars. The research that you do there is you can really measure the structure and ages of many of these white dwarfs, which are of course crucial also to discuss the evolution of the whole galaxy. So these can be used also in lots of other astrophysics. Here's from another paper on the subdwarfs, and this is specifically on understanding the binaries, where you really see many of the details in these subdwarfs being reflected in the binary system, and these are the type of data that TESS is providing on several stars across the sky. I won't give any reports from or highlights from the modeling, but this is of course an amazing development in the modeling of all these stars, because we are really in the modeling challenged by this quality of data. You have to explain these oscillations, the frequencies, the details of phase shifts in the oscillations, and the structure inside the stars are affected by this. So of course, the really way of learning this or inverting the data is through detailed modeling. And a lot of the researchers at the workshop were presenting updated models on physics, the assumption in the physics you put into stars. And if you thought we know everything about stars and the structures, you should attend these discussions, because there's so much unknown and it's really doesn't necessarily fit with the data we have. For massive stars, TESS is really opening up things that could not be done using Kepler. Kepler pointed away from the center of the Milky Way itself, and therefore many of the massive stars, bright O stars, B stars, were really very rare in the Kepler field. But for TESS, there's so many O stars, B stars oscillating, and just two examples of highlights from this: all the activities from the magnetic O stars. You see it in lots of frequencies. In fact, it's also clear here that the co-trending basis vectors are affecting what you see, but this is a detail. But the real thing is you can really study these effects from the interaction with the rotation. And this is a paper or this discussion presentation by Vincent van der on something that we have only really been possible to do in the sun until now, but the quality of data now becomes so high that you can start to invert the frequencies, and instead of modeling directly and just compare with the frequencies, you can invert the frequencies and then check for where are the deviations between the model and the structure that the sound speed from the oscillations will tell you, or the so-called G modes, which are buoyancy modes. And this is just one example, actually not directly from one of the TESS stars, but in a ground-based observation on a subgiant called New Hercules, where it's very clear that the model and the data do not fit in the core. The sound speed is simply different. So there's something strange in this core that might be exciting, or might just tell us that there's something we don't model correctly, of course. But this is what we have done in the sun for a long time, inverting the data and to see what the real sound speed structure is of the sun. Going into intermediate mass stars, which are A and F pulsators, they are so-called Delta Scuti stars and Gamma Dorado stars, and there's a lot of them that have been picked up here. Gamma Dorado star is a non-radial G-mode pulsator. Period is close to 1 day before the space missions. This was a terrible type of oscillations, because they often faced up with of course, the rotation of the Earth, and from observatories they were very hard to detect and measure. But TESS data are really nice for this. Solar-like oscillations which are stochastically excited oscillations in red giants and main sequence stars are really used for measuring properties of a large number of stars, and their TESS have again here been very useful, specifically in the 20-second data, as Roland also pointed out by work that had been done by Daniel Huber, that the 20-second gives of higher accuracy, but actually, more importantly, also much higher frequency domain, and therefore we can really measure the high frequency oscillations in many of these main sequence stars. And we can use this also to test masses that are being obtained in other measures. So we can really use the seismology to calibrate, in this case here, a paper by Paul Beck, or talk by Paul Beck, where you compared the red giants in Kepler and subgiants also with those from TESS, comparing the Gaia dynamical masses. And the conclusion in the paper is that there's a good correlation. I can see a lot of points that are not which following the line, which means that there's something we need to understand. Why are the masses differently? We normally say the seismic masses should be trusted, but we should test this, of course. But the number of solar-like oscillators that have been detected, which therefore can be used to study the details of these individual stars, is huge. Both in the 2-minute and in 20-second, there are in the test data now more than 4,000 detected solar-like oscillators. And just before the space missions, we had a handful. So this is really where the space missions have provided something completely new, and really allowed us to study many phases of stellar evolution. And finally, binary stars. This is just an example. This paper there, where you see these are the kind of details you can do when you have data like this. This is in binary systems, you have the tidally perturbed G modes, and you see it here. If I leave the microphone, you see it here. The oscillation. These are the oscillations on top of the binary. And then you see the oscillations stronger when you interact. So you have this gravity buoyancy mode that the amplitude is stronger at the orbital phase in half here. This is induced by the orbit, of course, or the interaction between the two stars. These are type of things you can follow and try to understand. And then there was, of course, also discussions on exoplanets. The focus of this conference is not necessarily the exoplanets, but it's very clear that the host stars of those exoplanet host stars that have oscillations, of course, we know so much more about these stars. So to me, these are highlights. You may say they are very technical, but they are really impacting the understanding of stars a lot from the type of data. And if you want to learn more, go to the TASC webpage. And there was 100 posters also. These are a few of them, and they are all on that webpage. So thank you.
So I'm used to thinking that planets are much more complicated than stars, with much more diversity and much more not understood astrophysics. But I might have to change my mind.
I think you should change that.
Yes.
Well, I tell my students that we actually study stars first and model them. And then when we come to the planets, I tell them now it's very easy, because equation of states, everything compared to the stars is easy.
But you have to admit that stellar astrophysicists are lucky that planets orbit stars, because otherwise you wouldn't have all this beautiful data.
Exactly. And we would not be here, actually, if the Earth was not orbiting the sun. So.
All right. That's a fantastic summary. And there was a lot of fine print on your slides, so it's a good thing they're going to be posted.
Yes, please post them.
Any questions from the audience?
Please attend everything in Hawaii. We will look forward to that.
That sounds good. Okay. All right. Now we're going to hear about TESS Office of Interest. We're kind of double header here because it was when we just. Oh, there she is. Oh. All right, so Katherine is going to tell you about how they handle the light curves from Spock.
Oh,
No? Oh, no, you're going to do.
I'm just talking about general TOI.
TOI,
updates for
okay,
extended mission.
good. And then Michelle will talk about updates from EM2.
Yep.
Okay.
So we're going to point to something. Can you just use this?
Okay,
So just look at the mic.
good to know. All right, can everyone in the room hear me okay? Enough, okay, try to project. All right, so I'm basically just gonna give a brief update on TOIs from the extended mission. And if you don't know me, I'm Katherine Hesse and I work on the TOI and vetting. And you probably get a lot of emails from me. Oh. There we go. All right, so just kind of an overview so far. We've got kind of three main categories that these TOIs fall into. So one's kind of from the first 2 years of the mission, which are the prime mission TOIs. TOIs from the second 2 years of the mission, which are the extended mission TOIs. Those are still actively being released. We haven't finished going through all the data yet with vetting, so we expect some more still to come. And then we have the faint search TOIs, and those are contributed from Michelle, and she'll tell you more about those in her talk. But yeah, so we are getting very close to 6,000 TOIs, so pretty excited. Let's find that one. All right. So just kind of looking at the TOIs, just kind of in period radius space, you can see we've got quite a large variety at this point. And what's particularly interesting is in this region where we would kind of expect to see kind of these longer period planets being found, we are starting to see some of those with the extended mission data, as you would expect from having more data. So the slides just kind of zooming in on that longer period range, and we can kind of see we're finding somewhat smaller planets that are longer period as well. So we're hoping to keep finding more of those as we continue looking. And then just some other cool things from the extended mission, we were able to get some more additional transits to single transit TOIs from the prime mission. And then we also found around 50 additional candidates to TOI systems that were released during the prime mission. And some cool ones in there, we found another candidate to, I think, TESS 11B. We found a second candidate there, and then we also found one in the WASP 132 system. And I believe another candidate in the TOI 700 system as well. So, yeah. Oops, went too far. And then just a big thank you to all of the vetters that I work with. This is a word cloud scaled by number of vets. So the larger the name, the more vets they have done. And all collectively, we've done 150,000 vets and always vetting more. So we wouldn't be able to release the TOIs without them. And that's pretty much all I have for my part.
Why don't we save the questions until after Michelle?
Sure. That works.
Thank you. So far, TESS has been spectacularly successful in finding a really large number of planets from the SPOC team, the QLP team, and members of the Exoplanet community. And what I want to talk a little bit about today is what we can expect in the next 3 years, specifically EM2. Now, the full details of the predictions that I'm going to be sharing are in a paper that I released earlier this year. So obviously I won't be able to go into a lot of detail today. If you have questions about specific types of planets you're interested in, I'm always happy to answer questions over email or even after this talk. But just to give kind of a very brief overview of how I make these predictions for the expected number of planets and the types of planets that TESS will find, I'm using simulations. So essentially, I start out with all 9.4 million stars in the candidate target list. So this is the subset of the greater TESS input catalog that is specifically stars most likely to be able to host planets detectable by TESS. Around each of these stars, I simulate a random planetary system. There could be 0 planets, there could be multiple planets, and each of these is going to have randomly drawn physical and orbital properties based off what we know from the Kepler mission. Then I simulate which of these planets would be expected to actually be detected by TESS. This is taking into account things like how many sectors a star is observed for, the total observing baseline, where the gaps are in the light curve, the typical noise properties of that light curve. And for the planets themselves, are the planets actually expected to transit as seen by TESS? And if they do transit, do we have enough transits in the data, and are the transits strong enough to be picked up by a standard planet search pipeline? So essentially, when finishing up one of these simulations, I get left with something like this. This is a period radius diagram showing the expected number of planets to be found. In blue are those that I expect at this stage in the mission, so following the primary and the first extended missions, and in orange are the planets that I'm expecting that TESS should find newly over EM2. So to look at some general trends, the top histogram is showing orbital period. So most new planets from EM2, similar to what we've already found, are going to be short period planets. And a large part of this is because we are going to be looking at some new sections of the sky for the first time. And we're also going to be re-observing a lot of stars that lets us find short period planets that are smaller. So we have more transits to be able to find those. But specifically, the number of planets with orbital periods greater than 20 days could actually double over EM2. So I expect at this point in the mission, we should be sensitive to about 1,200 of those planets, whereas over EM2, that number should double to about 2,400. If we look at the radius histogram, TESS is still going to find a lot of giant planets, which are the most common types of planets that TESS has found, but the numbers of small planets is going to significantly increase. Specifically, the number of planets that are smaller than the size of Neptune could actually double over EM2 from about 2,000 now to about 3,600. So I think a lot of these are going to be really scientifically interesting targets to look at, and TESS is really going to be able to improve that over EM2. Overall, at this point in the mission, my simulations predict that TESS should be sensitive to about 8,400 planets, and by the end of EM2, that number should increase to about 12,500. So in other words, we should expect about 4,000 new planets detectable over EM2. A lot of this is really thanks to just re-observing a lot of stars, getting more data. That means more baselines, that means more transits, and that lets us find longer period and smaller planets. Now, of all these planets, about 200 of them I place in the optimistic habitable zone, and 20 of those are going to be smaller than twice the size of Earth. So these could be potentially rocky Earth-size or super Earth-size planets, which are of course of great scientific interest. Now, all of these I find are going to be still orbiting M dwarfs, but hopefully with future extended missions, we'll be sensitive to planets that are really small around sun-like stars. So one thing that's interesting to look at is how does the actual TESS yield compare with these simulations? If there are major discrepancies between these two, this could indicate that either the simulations are doing a poor job of reflecting the TESS yield, or it could mean that current TESS searches are incomplete. So on the left-hand side, I'm showing all of the TOIs once you remove the false positives. That's leaving about 5,000 TOIs. And on the right side is what I'm expecting at this point in the TESS mission, which is about 8,400 planets. Now, the main discrepancy that I found when looking into this question is just that I think that searches of the FFI observations are not complete. Even if we look at kind of the most major FFI search pipeline that looks at the TESS data with every single sector, that's the Quick Look pipeline, which has produced most of the FFI TOIs so far. QLP is limited in its search by looking at planet candidates around bright stars, so those that are brighter than 10.5 magnitude. And we're also limited in our orbital period search, which is only up to about 60 days. And the reason for these is just because there's an enormous amount of computational resources needed to search such a large number of stars. And there's no single planet search pipeline looking at the FFIs that is able to search all 9.5 million CTL stars really comprehensively. Now, there are a few things that QLP is doing to try to bridge the gap in the FFI observations from the actual yield to the expected yield. The first one, as George mentioned, is that we're going to have a GPU-based planet search algorithm, which is going to significantly increase the speed of our current planet search. This is going to allow us to use a finer frequency grid, which will be able to capture planet periods much more accurately and precisely. And we're also going to be able to extend our planet search out to longer orbital periods and kind of fill in that space where TESS hasn't found as many planets as expected, following on from what Katherine said. A second update is that we've improved our automated vetting routines. So a really big reason why looking at so many stars is a good problem to have is because once we have our pile of detections, we then need to look through these hundreds of thousands of detections to identify the planet candidates. And so we rely on automated vetting to do that. So Astronet Triage is a machine learning classifier that QLP uses following our BOS step. And there have been some major improvements to the performance of Astronet Triage. And so you should be able to see an upcoming paper led by Evan Tay here at MIT, and I know he's in the audience, and Dan Moldovan at Google. So we're going to be describing our improvements, mainly thanks to a larger training set, more complete labels, and we have improved accuracy across the board when compared to our older Astronet Triage. Now, another planet search effort that I want to highlight is the faint star search. So this is co-led by myself and my collaborator, Tansi Dalen, and our whole motivation was recognizing that QLP is magnitude limited to only look for candidates that are around those brighter stars. So we wanted to look at the fainter stars that a lot of FFI search pipelines don't tend to focus on. And as a result, we've so far found about 2,500 TOIs, which is over 40% of all the TOIs that have been found by TESS so far. So I'm really proud of this effort. Most of the planets, as you can see in this plot, are hot Jupiters, which makes sense because as you get to fainter stars, their light curves are going to be noisier, which means it really helps to have a lot of transits and really deep transits. But as we're getting more data from TESS and looking through later EM1 sectors, we are finding that our planet candidates are getting progressively smaller as well as longer orbital period. So even around faint stars, I think there's a lot more we can learn. So I think if there's one major takeaway from this comparison, it's that we really haven't exhausted all the planets that can be found with TESS, even with the data at hand. So there are more independent planet searches, specifically of, I think, the FFIs that could really help kind of bridge the gap between our actual yield and the expected yield. And specifically those that are optimized to find long period planets, I think will be able to produce a lot of exciting candidates. So if any of you are sitting here today or listening and are concerned that, you know, everything's already been found, so what's the point in getting into the planet search game now? I think that the answer is loud and clear that we can all, you know, help find a lot more planets with TESS, and there's a lot of interesting science that TESS can do with these. I do want to highlight one section of this plot before I wrap up here, which is that there's one area of parameter space where TESS is finding a lot more planets than we expected, and that's the Neptune desert. So if you look on the right side, you can see there's that kind of empty region, which is intermediate sized planets at short orbital periods called the Neptune desert. And the reason it's empty in my predictions is because Kepler found almost no planets in this regime. So that means my predictions are that TESS would also find almost no planets. But TESS so far has found hundreds of new candidates in the Neptune desert. Of course, inevitably, some of these are going to be false positives, but even if one or two of these candidates are real, that is filling in a space that we really don't have a lot of data. So I think that what this shows is specifically for short period planets and large planets, including those in the Neptune desert, TESS has an enormous amount of statistical power to better understand the characteristics of these exotic planets. So I'm going to leave up my takeaway slide here and take questions.
There's a lot to absorb there. So, Katherine, I'm wondering if the rate of new TOIs that we're getting now from the end of extended mission 1 and soon from extended mission 2, is that rate what you expect from the simulations? Are we getting as many as you predicted? I don't know who's going to answer that.
Yeah. But I think my main takeaway is that we need more broad searches of FFIs to really kind of match the predictions. I will say one thing that I didn't mention, just out of interest of time, is that when you correct for the fact that QLP searches for planets around bright stars, this is a comparison of the primary mission yield when you only look at those bright stars, and my simulations match the actual TOIs almost exactly across spectral type, planet radius, orbital period, and TESS magnitude. So I do have reason to believe that the simulations are working. They are able to reflect the TESS yield under the assumption that there are complete searches of every single star that is in the CTL. And that isn't reality yet. I think as we get better planet search algorithms like the GPU, that is going to be a lot faster. That's really going to help us kind of bridge that gap. So I'd say like wait and see over the next few months when we implement the GPUs. I think that'll really help.
So at the beginning of the mission, I designed my follow-up observing plan scheme to accept a limit of 9,999 discoveries, and I'm going to have to change it. I'm going to have to change that, and why? Okay.
I think just over the last year and a half, we've more than doubled the TOI yield, so it's getting there.
Yeah, but a lot of those were the faint ones, I think.
Yeah.
Mm-hmm. They came in large batches.
Yes.
They're still coming.
Yeah. Do we have any? Okay, we're going to cover with Andrew and move to the right. Andrew?
How many of the discovered the planets or the stars fainter than you all think star search? And do we need like a really faint star search?
Do we need a really faint star research that goes fainter than 13.5?
Yeah, so just to repeat the question for those online, the question was how many of the planets that we're expecting to detect are around the fainter stars that QLP currently isn't searching, specifically those that are fainter than 13.5 magnitude. So most of those planets obviously are going to be the M dwarfs, which are kind of, I think the CTL looks at other types of stars brighter than 13th magnitude, but anything fainter than that will be the cool dwarfs. So one update I can share is QLP recently changed our selection criteria for which target stars actually get light curves. And so for general stars, we're looking at brighter stars, brighter than 13.5, but we are actually including fainter M dwarfs in our FFI target selection. So those are getting searched, and theoretically they should show up in the faint star search. So yeah, I think it's really the kind of the fainter M dwarfs is where the major yields are going to be. Most of the planets that we should be able to find are still around kind of the brighter ones, just because that really helps planet detection. But again, I think that the changes QLP is making will help kind of bridge that gap for M dwarfs.
Let's see, Josh next, and then we'll move back.
So the results that you're talking about here are applicable to the FFI light curves with QLP, but QLP is only one of many different child cyclonic light curves from the different times. There's spot, there's inline ones, there's the other light curves. To your knowledge, has anyone compared the expected planet discovery performance from the different FFI pipelines to know whether there would be some benefits in certain areas of parameters based on some of the FFI pipelines versus the others?
So the question, the question was the simulations have kind of focused on QLP as the main FFI pipeline, and if there are efforts to compare the different FFI pipelines for completeness. So for the just a first note is I didn't assume that a QLP like FFI search pipeline would find planets. I assumed that just we're looking at a long period planet search and we're looking at all the stars. That doesn't reflect any individual FFI search pipeline. You can consider these yields more like how many planets are theoretically detectable. The yields that I kind of showed here, which I didn't have time to talk about, that's if you restrict the subset of assuming a QLP like FFI pipeline, then the yields will go down. But to answer the actual question, which is about comparing different FFI pipelines, I'm not aware of efforts to do that because as far as I'm aware, there isn't actually a search completeness characterized for any FFI pipelines, including QLP. In order to do that, we would need to do injection recovery tests. We would need to simulate planets versus false positives and characterize the pipelines. And I don't think any FFI search pipelines are fully automated enough to be able to do that in a robust way.
Well, Christo, and then we'll go online.
Really nice talk. When I looked at the expected planet yield as a function of planet radius, I noticed that it seemingly very low expected planet yield for planets smaller than Earth. Is that because of the limited sensitivity in those simulations, or is that because of the underlying assumptions on the occurrence rate based on what you have?
So the question is, if you look at kind of the planet radius histogram or the yields of small planets, there's a very low number of smallest planets here. So is that a consequence of maybe the search completeness of tests, or is it a consequence of decisions made in simulating the planets in the first place?
Yes.
I would say it's a little bit of both. So in terms of the occurrence rates, the small planet regime, even with Kepler, is really hard to characterize. Even small changes in your completeness characterization can significantly change how many planets you expect for the low number of planets. So I think in my case, I found that the occurrence rates that best were able to reproduce the primary mission yield when I was kind of comparing the benefits of using different occurrence rates. That one happened to have kind of lower small planet yields than some of the other pipelines. So that could have something to do with it. But I think that a second thing is that the smallest planets really need low precision light curves from TESS, and they also need high transit planet radius to stellar radius ratios. So we really are helped in the M dwarf regime by finding the smallest planets. So the smallest planets by TESS are going to be found around M dwarfs. And I think, yeah, I think it's just, it's a bit of both. It's hard to find small planets, and it's also hard to characterize the occurrence rate of those planets because completeness is so low.
And if you're wondering why Christo asked that question, listen to his talk starting at 10 o'clock tomorrow morning. And we have one more question. I think we can.
Sure, I'll just quickly add, if you look at the comparison with the primary mission yield, it looks like the TOI yield is a little bit higher than my predictions. So my predictions might be underestimating the small planet yield a little bit, but again, it's hard to simulate in that area.
Okay, everybody can read Peter's question, the bump. The bump. In
This one.
planets a period of 2 years in the previous diagram, okay. Due to alias 1 year period, or is it due to 1 year period, or are those injected periods?
So this pile up here, I'm assuming that's what the question is
Yeah.
referring to. This is actually a 2-year period.
It's 2, yeah.
And that's just because stars are reobserved. So one star might be observed in year 1, and then 2 years later in year 3. So we don't know the actual period of these signals. Our best guess is that we can measure the longest time span between those two, which will be about 2 years. But yeah, that's why there's this pile up here. They're likely shorter period planets.
Yeah, a lot of those will happen to catalog the longest possible
Right.
period, and then a comment that
Yeah,
it's
and then
likely shorter.
they get follow-up and they have a shorter period, yeah. All right, excellent talks. Thank you very much, both of you. Now, Sam Quinn is going to address the issue of planet candidates that actually end up with masses. And why are there so few of them compared to the number of exoplanet candidates?
Well, Dave, hopefully I will convince you there are not that few. Yeah, so I'll be talking a bit about the exoplanet yields, the true exoplanet yields in terms of those that have been confirmed with mass measurements. Of course, planets can be confirmed or validated in other ways. They don't need a mass measurement for us to be confident that they're real. but I'll be talking specifically about the effort to get masses from precise radial velocities. So before I start though, I just want to acknowledge that first of all, it's a real pleasure to give this talk on behalf of the whole TESS science team, and especially the TESS follow-up observing program, which involves hundreds of astronomers. You'll hear more about that. And it's really due to the hard work from all of you, and ultimately the last step, the PRV teams to measure the masses, that we get to talk about the science that we can get out of TESS. Okay. So I want to take you back in time. It's April 2018, and everyone's excited about the promise of TESS. And in particular, there's one specific promise that was codified in the level 1 requirement of measuring 50 new masses of small planets. Of course, we've joked at times that there was no requirement about the precision with which we would measure those masses, but as we're all interested in the science we can get out of them, we've done our best to measure precise masses. And there's sort of some more informal promises made that people were excited about, that the planets found by TESS would be prime targets for JWST, for atmospheric observations, that TESS as an all-sky survey will find planets in new parameter spaces. And you heard Michelle talk about the hot Neptune desert, for example, and the promise of finding new planets there. And also there was talk about the smallest planets being around M dwarfs, and because it's an all-sky survey, TESS will be able to observe the brightest and nearest M dwarfs and detect small planets around those. And given the time baseline with which TESS can observe some of these stars and revisit them, many of those may end up being temperate worlds. And again, you just heard Michelle talk about her expectation that there will be many habitable zone candidates soon. So let's see where we stand now, more than 4 years later. Now, we also talked about that the publication rate from non-exoplanet science is outpacing the exoplanet science. So I might have to convince those of you, the 60% of you who are publishing stellar astrophysics, that we need to study planet masses, and in particular, precisely measured masses. So in this world where we're in 2018, we don't have any TESS planets yet. So it's a bleak dystopian world. Okay, it's not this bad. I just wanted to show a blank diagram here first to orient you on the axes and the colors and the models, because I'll be talking a bit about this diagram as we go through it. So here we have a radius as a function of mass for the planets, and overplotted are several models. These are from Li Zhang, and they show the expected for different compositions where you expect planets to lie in this diagram. So 100% iron, Earth-like composition, which has an iron core and a rocky and bare rock with perhaps a thin atmosphere. Water worlds, which are on this particular model, there's a 50% water, 50% rock model of pure water, which of course is not a realistic composition for planets. And then some rock covered by various mass fractions of hydrogen. So 0.1%, 1%, 2%, 5%. These models are evaluated at effective equilibrium temperature of about 1000 Kelvin, just to guide the eye. I've also plotted the solar system objects on here, Venus and Earth, as well as Uranus and Neptune. So what does the world look like without TESS planets? Here are the currently known, and my plot's a little bit out of date, so if you don't see your favorite point down here, I'm sorry. There's probably a handful of planets that I have not included on this plot, but these are non-TESS discoveries with better than 5 sigma mass measurements. Remember, we want precise masses for a number of reasons. One, because you can understand the compositions of individual planets better. It allows you to interpret other follow-up observations like atmospheric characterization. And you can see population trends if you have precise mass measurements. So you notice a few things about this diagram. First of all, I didn't include the TTV planets, so there's not a nice string of precisely characterized TRAPPIST planets down here. But there's kind of a hodgepodge of planets here. There we see this the radius valley, some planets larger than 2 Earth radii and a few smaller than 2 Earth radii. These ones appear to be rocky, but they're all very hot, and that's a consequence of many of the host stars that we around which we detected planets with Kepler, for example, were either more massive, like sun-like. So those late type stars were not very numerous in Kepler. That's changed a bit in K2. And also fainter. So in order to measure masses of small planets, you need a lot of photons. And so if you have faint host stars and more massive host stars, you're going to be limited to what you can do a reasonable amount of telescope time. So some trends are maybe starting to emerge here, but it's unclear whether this region in here is going to fill in with planets as we expand our parameter space. So let's get out of this this dystopian world and head back to reality. So this is the non-TESS planet masses currently, minus a few, I'm sure. And here we have the TESS planet masses measured to 5 sigma or better. I'll say right now that we have, at the end of the prime mission, we had surpassed the level 1 requirement of 50 masses. We're now at 100, exactly 100 published or posted on archive masses of planets smaller than 4 Earth radii. This plot is 5 sigma masses, so that there are 70 better than 5 sigma currently. And the first thing you see is that, yes, parts of this plot have filled in, especially down here for these smallest planets. You might also notice that the temperature of the planets, especially these small ones, is a lot cooler. So the blue dots are the cooler planets and the red dots are the hotter ones. And so here from TESS, we're getting these small rocky planets that are not just ultra short period and baked by their solar-like stars. So we can combine all of them together. This is now all sources of 5 sigma or better mass measurements. And I think some really interesting features start to emerge. Now I could spend a long time on just this diagram alone, and I want to get to a few other things. But I'll point out, a few features that you can start to notice now that we have a nice sample of precisely measured masses. The first is this this truncation here at this around 10 Earth masses for this Earth-like composition. So there are no bare rocky cores more massive than 10 Earth masses. So that's telling us something, I imagine, about formation process and when runaway accretion occurs. But also you have this large group of planets now with a range of masses similar radii just above the radius valley. And so the question is, what are the compositions of these planets? And now we have these precisely characterized planets that we can further study in order to understand more about these populations. In particular, if these are covered, if these are gas enveloped worlds, then that means that their cores, this is 0.1% hydrogen by mass. Then if you remove that hydrogen, then you should have more massive cores down here. So these could be a different composition, for example, water worlds. But now we get to study them in detail. I hope it was clear as I was pointing out all the various regions of parameter space covered by Kepler planets and TESS planets, that this is not an unbiased sample. So don't do statistics. You can gain insight from it, but if you like populations, stay tuned for the demographics working group discussion later, led by Jesse Christensen. And then also some talks I noticed coming up about some various subpopulations of planets that may be easier to work with in a statistical way by Christo Ment and Sammy tomorrow. Okay, so now we have lots of precisely measured masses from TESS and other surveys too. I don't want to downplay that, but now the masses, precisely measured masses, are dominated by TESS planets. So are they actually well suited for JWST? So I'll just do one slide on this because I know there's going to be some interest and some discussion from other people coming up in this meeting. But yes, TESS planets are among the best JWST targets. So on the left, again, I'm showing the TESS small planets with precisely measured masses. And then on the right, I'm showing TESS planets in blue and non-TESS planets in gray, with the transmission spectroscopy metric devised by Eliza Kempton and collaborators as a function of radius. And so you can see at all radii, TESS planets lie along the upper envelope of the TSM, suggesting that if you want to study planets at any given radius, then TESS planets will be among the best, the most accessible to James Webb. So we found lots of planets. There was a promise that maybe we would find planets in new parameter space and new environments. So rather than talk about all those environments, I want to focus on one thing, which is expanding the sample of host stars that host precisely measured host planets with precisely measured masses. So starting on the left here, so the G dwarfs, we have TESS on the top and non-TESS on the bottom. So these are mostly Kepler and K2. And you can see that, there were a fair number of planets here, but we've certainly greatly expanded the sample with TESS. And perhaps some features can start to emerge as you combine those samples. Similar for K dwarfs, a similar number, it looks like, from TESS and non-TESS planets. But then this expansion into M dwarf parameter space, which I'm really excited to see, for example, Christo's talk, but also there were some really exciting results that came out recently from Rafa Luc and Henri Paillet, where they examined M dwarf planets and suggested that rather than two separate populations, there were three separate populations with distinct densities, so rocky worlds, water worlds, and enveloped worlds. And it's they've certainly done a more careful job of the M dwarf population than I have here. I'm simply taking published values and throwing it on a plot. So that's the sort of science that you can do as you expand to new parameter space. And so I just want to, with that in mind, I wanted to look at the K dwarfs real quick. So this suggestion that there are three populations, I think is an interesting one to look at now that we have this rather large sample. This is all planets, both TESS and non-TESS planets, using the same precision cutoffs that they used in their work for M dwarf planets. So 25% mass uncertainty and 8% radius uncertainty. And to my eye, it looks like there is indeed a population of planets that lies along the Earth-like composition curve, another population of planets that's consistent with this 50% water composition curve, and then a third with gaseous envelopes. And so you can highlight those there, and they separate out pretty well in density the same way that the study from Rafa and Enrique showed for M dwarf planets. So I think these sorts of studies are the ones that we'll start to see now that we have this large sample of precisely measured masses. I'm really excited to see what everybody can do digging into these populations now. I did want to mention that there are plenty of giant planet discoveries and some really great work going on there. This is a paltry haul compared to the non-TESS planets for giant for large planets, but it is expanding into new parameter space in terms of orbital period, in terms of host star properties, and you'll also see, I think, both for giant planets and smaller planets, as Michelle mentioned, longer period planets becoming a real focus as the second extended mission and beyond continue to discover those. And I think there'll be a nice talk from Paul Dalba about some of the work going on in the single transit working group. So I'm going to leave it off there and just say that, tying back to our question from 2018, have we delivered on the promises from TESS? Well, the formal promise, yes, we have 100 precisely measured masses of small planets. Again, this is entirely due to the industrious folks in the TFOP working group and the community beyond. So I would like to give you all a round of applause for really driving this effort, and it's been fun to be along for the ride. And I'll leave up the other conclusions. I think the presentation went through those. So thank you.
So can we really do demographics by the end of extended mission 2?
Well,
We're
not-
seeing the hints now of what's there.
Yeah, I think, like I said, these are not statistical samples, unbiased samples of mass measurements. Rather, a lot of the demographics work will come from independent efforts. But there's obviously a lot we can learn about planets by formation and evolution by studying those with measured masses.
And if you're going to include brown dwarfs as kind of planets, there's been a real revolution there. We've almost tripled the number of transiting brown dwarfs.
Absolutely.
Okay, questions from the audience? They're all ready for lunch. Oh, there's one online.
Okay, so Connie asks, which fraction of your planets have astroseismic ages, radii, and masses? I would imagine very few. Help us out. Ages are so important. I called out young planets on my final slide here. There's been a lot of wonderful work on young planets and understanding what we can learn about planet evolution by studying planets at a variety of ages. And astroseismic ages and other stellar properties would be fantastic for a larger sample of these planets.
Okay, it's lunchtime. Be back here at 1:30.
A few announcements.
And Avi is going to keep us honest here.
So a few things. So I remind the speakers to upload your files if you haven't done so already. The link to upload is in an email I sent you, and it is also on the wiki page, which should be right here. So this is the Dropbox link to upload your files. Once you do, you will receive a confirmation email, meaning you didn't receive the email, you didn't upload your files. So let me know if you have a problem. Second, we are going into a lunch break. We'll be back at 1:30 p.m. Eastern time, local Boston time for those online. For the people in the room, in the table back there, there are some extra outlets to charge your anything that needs charging. And we also have some water on that side next to the coffee. And finally, we do have a small map with restaurants in the area. There is a printout on the front desk, and it is also on the webpage down here. And it's not showing up. Maybe it will. Maybe I just need one click. Anyway, you need to trust me that it's right there and you click on it. Maybe I'll remove this. And yeah, sorry, this is not showing up here, but you can see it on the website, and you can take, if you want to print out from the front desk. It's really in the next block over to the south. There are a few restaurants, so you don't need to go far, and be back here at 1:30. Thank you.
Avi?